the boundary value problems for the ordinary differential equations. And today, if I'm not mistaken with the numbering, the paragraph number is 4, and we'll talk about the finite element method. You might have heard about this method in various contexts because it's very popular, especially now. Here a special course is taught based on COMSOL software, and COMSOL is totally based on the finite element method rather than finite difference or any other technique. So a finite element method is newer approach for solving boundary value problems numerically as compared to the finite difference approach. Actually, if taught properly, it involves more complicated mathematics. But we will stick with simpler concepts, and I will try to formulate the ideas using simple words without using functional analysis or things like that are usually used to formulate the finite element method. So, what's the idea? Let's take an example problem as usual. For example, we have a problem like this. We have a glass at temperature T1 poured in some bowl, and we have a small tube, we have a small hole in this bowl from where the glass goes down. So we are interested to know the temperature distribution. Let's say we have the x-axis here, and we are interested to know the temperature distribution as a function of x in this stream of glass. In real glass processes, this glass is surrounded with some environment usually, and this environment has a temperature T infinity. So the glass exchanges heat with this environment, and let's assume that this heat exchange is convective, and H is the coefficient of heat exchange. So H is heat transfer coefficient. H, heat transfer coefficient. Heat transfer coefficient, its dimension is watts per meter squared Kelvin. Unlike the conductivity. In conductivity, you have meter in the denominator rather than meter squared. So this coefficient says how intensive is the heat exchange between the environment and the glass. And this intensity of heat exchange depends on the nature of the airflow around the glass in the environment. The more intensive the airflow here, the higher the value of this coefficient. Typical values, just for your reference to have something in mind, the typical values for this coefficient, if we had a flat sheet of glass placed vertically, it would induce the airflow, turbulent natural air convection, which would lead to the value of 8 approximately. If you pump air for the reason you especially cool down the glass with some ventilators, you could get the values of H of about 50. No more than 50 actually. So let's assume also that at the bottom of this flow, somewhere like 1 meter of flow or 2 meters of flow, and then we want to cut the stream of glass. How do we do that? Usually, people just cool it very intensively with a directed airstream, air jet. And this would involve another coefficient of heat exchange, just like similarly to the side surface of the glass, and some other temperature. I call it B because I want to denote this point B on my axis. This is point A. Or maybe 0 and L to make it simpler. Like this. We should write L here and L here. This H would be much higher than this H because we have to quickly cool down the glass to produce thermal stresses which would lead to breakage of the string. So glass just breaks here. So and this is how we get this computational domain from x equal to 0 to x equal to L. So what is the equation that defines the heat exchange here? I need another quantity also. This quantity is the rate at which glass goes down. This rate is connected to the velocity of glass. I don't want to call it velocity because its dimension will be a little bit different. So we have the equation like this. Well, let us say that u and t in this context is the same function. I just denote it in a typical way with u, as I did before. Plus q of x du by x plus r of x u is equal to f of x. This is the equation that we would get if we rewrite all this physics and this coefficient and this right-hand side depend on this physics of heat exchange from the side. So these two terms represent actually this convective heat transfer from the side. Because the convective heat transfer from the side, this Q, it will depend on X, what it is. It is H, the heat transfer coefficient, by the temperature of the glass at this particular point, minus the temperature of the environment. So the hotter the glass, the higher the heat sink, the convective heat sink. Okay? So this heat sink just goes to the right hand side, and if I denote H multiplied by T, if I take it to the left hand side, so H will become my R with the minus sign. Okay? So, speaking abstractly, what conditions we need to ensure to be sure that this equation has a unique solution, has a solution? First of all, this R of x should be what? Do you remember? More than 0. And we discussed why. Otherwise, we would get a positive control in the system. This Q can be anything, actually. It can be positive or negative. In our particular case, it's positive, right? Because the velocity is directed downwards together with our axis. What else? So, in the beginning of our domain, the domain is from 0 to L. In the beginning of our domain, we have the condition. It is a known temperature, right? So it is the first type boundary condition, the fixed value of the function that we are looking for, that we are searching. on the other end, we have the following condition. This is the heat flux that goes out of the glass. And what defines this heat flux? This coefficient of heat transfer, HL, and the difference between the temperature of the glass at point L minus the temperature of the cooling air. Let me check that I didn't that I wrote the sign correctly. Yes, looks like that. The sign is correct. So this is our differential problem. So we have one condition of the first type and one condition of the third type. This is the third type boundary condition because it involves the derivative of the unknown function and the unknown function itself.
I have a question.
Yes.
What's for mu? What's for TL? And is one for gas? Is one for air?
Could you say it again, please?
I say the mu x equal to L. What's different with the TL? TL is the point. Is that point?
I denoted with TL the temperature of the external air.
Yes, it's for air.
That you are using to cool down the glass, and U at point L is the temperature of the glass. Okay. So to make it more standard form of the third order of the third type boundary condition, I will move this term with the unknown to the left hand side. Minus HL multiplied by TL. So this is the same thing, right? So here you should recognize that this is the third type boundary condition. Okay. We can denote the function or the quantity on the left hand side of this equation with some formal operator notation. We can say that some formal operator, differential operator L, is acting on our function U. And it is producing another function as a result. So this L just defines the algorithm that we are using to convert function U to the functions standing on the right hand side. And as for the right hand side, so let me see. For the right hand side, we don't need to do anything. So if I introduce this notation, I can say that I have an abstract equation of this form. Some operator is acting on my U and converts it to F. And I can also put everything on one side of the equation and denote the result of this movement as another quantity, the residual function, or residual operator, actually. Residual operator is like this, and it should be 0. This is what we want. So these are equivalent transformations. I don't do anything. I just denote things with different letters, right? So we have some residual, and it should be 0 for every x from 0 to L. It's possible to look into this problem from a little bit different angle. Actually, people don't like that this second derivative acts on our unknown function, because this unknown function may not be smooth enough. In physics, we can have this situation, for example, that our glass changes its state at some point here abruptly, and it changes its properties abruptly. It may be related to some physics involved with the glass composition, or it may be involved with doping that we can introduce in the flow, right? So, and if this happens, this p of x will not be a smooth function. P of x is actually has a sense of thermal conduction coefficient, right? And you can do something to abruptly change your thermal conduction. And if you do so, this derivative would not exist, because you cannot differentiate discontinuous function in classical sense.
The x.
Yes. You cannot differentiate this p of x multiplied by du by x if p is discontinuous, right? So mathematically it would mean nonsense, this derivative. But this is a very common situation in real life, that this coefficient changes abruptly. So
not the second derivative of the u. Not the second derivative of the u function changes abruptly, but
not the secondary, but as you can imagine, in real life, this u will also feel and change its behavior because of the abrupt change in the thermal conduction coefficient. It should become less smooth function, and it also may not have the second derivative, right? So we have this situation. In real life, we can have such problems easily, and can make a system that behaves like that easily, but mathematically we are not able to describe this problem, and we don't like that. The problem is with this external derivative. If we did not have this derivative, we wouldn't have such a problem, at least here, right? That's why we want to reduce the requirements for the smoothness of the functions that are involved in this equation. We want to allow for less smooth functions. How to do that? This idea is called a weighted residuals method. The idea of reducing the smoothness. We can say that we will satisfy this equation, r of u is equal to 0. Not exactly, but in some weaker sense. What means a weaker sense? For example, we can say, let's request that this integral, well, let's start from this, that this integral is equal to 0. So we can just square our residual and request that this integral of the squared residual is 0. Well, if you are good in mathematics, you should know that this means that the function r of u of x must be 0 everywhere except possibly for some countable number of points in our domain. Countable, it means that we can count the number of these points where it is not zero, right? So it is approximately the same as this condition, but a little bit weaker. We allow for the function r of u of x to depart from zero in a countable number of points if we request this. Do you agree? Okay. But if we do this, if we take this approach, practice shows that it will lead us to an uncomfortable matrix in the past. That's why people don't use this approach. But what they do, they say, let's multiply our residual by some function v, which is sufficiently smooth. Okay, and let us integrate it over the interval of interest. If this function is sufficiently smooth, then requesting that this equation holds true is also similar to requesting that the original equation holds true. And if we take a little bit higher in the stairs of mathematics, this operation may be called taking a inner product or a scalar product of this function standing on the left-hand side of our equation and the function v. So this integral actually defines a scalar product between r of u and v. I should have written it. It is just a notation for this integral. It is scalar product. If you recall linear algebra, what the scalar product means, there are three axioms that the scalar product must satisfy. And you can check at home that this definition of the scalar product satisfies all the axioms of the scalar product. That's why we can name it like that and use its properties. Okay, so what we do is we weight our residual with some sufficiently smooth function, and we request that the scalar product of our residual and this function is zero. So this is the keystone component of the finite element method, and many other methods that can be derived from this idea. Okay, let's continue then. So we just multiply the left-hand side with some function and integrate it, and multiply the right-hand side with some function and integrate it, and request that these two integrals are equal. You follow?
Yes.
Any questions at this point?
Maybe why r squared integral of r squared should be just greater than zero? Like r is, we said that r in some points can be not zero.
Yes. And still this integral may be zero. So well, it is like first grade mathematics course in high school. So you can change the values of a function in a countable number of points, and the integral of this function will not change, because the integral is something that involves averaging, local averaging at every point. And if you change this function, say at one point, it changes nothing because the surface of this figure, of this rectangle, will not change if you only change one single point. It does not have any length of support, this point. Do you see? How the integral of a function f of x is defined? Do you remember? The integral is a limit of the Darboux sums of a function. It's like a заклинание. I don't know English for заклинание. So f of xi by hi, where hi is the length of this interval, and we should tend it, right?
In this case, f from xi, because it's squared, it's always positive.
Yes, it's always positive, so it must everywhere should be 0.
Why it should be 0?
Because it's how to say plus
So it's positive, so the sum of positive numbers is like positive numbers.
Oh,
Alexander, if you change r of u in one point,
Yeah.
how long is the part of the x-axis below this one point? It's 0, right? So when you try to account for this one point in your integral, you have to multiply the value by 0 length.
Okay, so it's not the короче, это не участки, а буквально точки.
Да, если вы в нескольких точках, в счетном числе точек, бесконечном, но счетном числе точек, как в натуральных числах там, или в единице или натуральных числах, тогда ничего не поменяется. Но это как бы некая фундаментальная вещь. So, okay. This whole discussion was just to illustrate that this approach weakens the requirements for this equality. We are weakening this equality, right? We are making it less strict, so to say.
So if how do you say if it satisfies this square integer, it must to be 0. But if it is be 0, but maybe it not satisfies the square integer.
Yes. So if some function satisfies this, it may not satisfy this exactly.
Yes.
Only
it must be everywhere be 0. It can be 0.
almost everywhere. Mathematicians call it satisfies this condition almost everywhere. By almost everywhere, they have in mind, or they understand that it may be different in a countable number of points. Okay, but let me stress this. I took this example with the squared residual only to show one possibility. The finite element method does not take this possibility. As I said, if we take this possibility, it would lead us to the matrix that we would not like. Okay? That's why people use a different approach.
Yes, it will be more.
It will be more useful
Yes.
in the context of the finite element
It
method.
is less condition.
So, here you might want to ask me, what is function v? What space it should belong to? Let's say for the moment that it is from some linear space v capital. And we will define what this v capital should be a little later. Because when we say that we multiply something by some smooth function, we have to explain how smooth it should be and say other words about this function. Okay. Okay. So let's do this. So we have an integral from 0 to L from this first term, right? Minus d by x, p of x, du by x, du by dx. And we need to take this integral separately because the most work will be related to this term. All other terms are just rewritten. Oh, I'm sorry. I should have multiplied it by v of x. Forgot. So multiplied by v of x by the alpha. This guy is called a test function. In various sources, it is called either test function or weight function. Weight function. And the rest of the left-hand side is also integrated like that. Multiplied by v plus r of x u multiplied by v dx. It is equal to, I will delete part of the boundary conditions here because I don't have space. But I will keep, I will do this. I will say that x equals 0 is equal to t1. I just freed up some space for me, but I will need these equations later. So, and the right hand side is just integrated directly. That's it. So, this is nothing but integrated equation star. And next thing we want to do with this, what do you want to do with this? If you want to reduce the requirements for the smoothness of P and U. This is the second derivative under the integral. And it is multiplied by the function sufficiently smooth, which is not differentiated. So people who want to reduce smoothness requirements for P and U should use integration by parts here. Do you remember what is integration by parts? uv on the limits minus integral v du. Unfortunately, we should replace v and u in this formula for our purposes to make it easier for us. This is the same, and here u, here v. And this. So the v here is exactly the v that stands here. Okay? And since this is the derivative by x, we can move it under the differential. Right?
Yes.
What will happen? Let's do it. Let's do it explicitly. P of x du. No, sorry. That's not what I wanted to do. I should write v, just like here,
Yes.
and then d of what? Of p of x du by x. Minus. Here, I kept it. Let's work just with this first part for the moment. Let's skip the rest of the equation and work just with this first part. So, what should we write about this? According to that formula, this is minus p of x du by x multiplied by v on the limits from 0 to L, correct? Minus, but we have another minus here. That's why this minus becomes plus the integral from 0 to L of what? Of p of x du by x dv by x dx. Do you agree?
Yes, yes. We only use it that way.
Correct, right?
Yes, yes.
Okay, let's continue. This term is something that we don't know yet. But what do we know about our functions on the right-hand side? At point L, we have the boundary condition here. Look here.
Yes.
Right? So we can rewrite this boundary condition back a little bit. I rewrote it before moving this u to the left-hand side, right? But I can do the opposite now.
Plus plus.
Just a second. Minus p of x du by x at point L is equal to let's denote this guy by eta, just by eta, okay? To make life a little easier. So yes, so it is eta plus HL u at point x equal to L. Now we can simplify this, just u of L.
Yes.
Okay. So let's substitute what we got there. Maybe I should write index L here with eta to stress that this corresponds to the right-hand side of our domain. Plus HL u of L. Okay. And V, and V also. V at point L. Plus H L U of L V of L. That's it, right? Minus. But we don't know anything about the derivative of our function on the left-hand side. Right? And here comes the trick, which strictly speaking requires justification. But I don't want to spend much time, I don't have time to just justify this trick. I will just say that let us insist or let us require that the function v is 0 at those points where we have first type boundary condition in our original problem. So in those points where we have the Dirichlet or the first type boundary condition, let us request that this function v is 0, our test function. X equal to 0. If we do so, we reduce this set of functions a little bit. So we take only those functions that satisfy this additional condition. If we do so, we will see that in this product, v of 0 is 0. Because v of 0 requirement. Because of v of 0 equal to 0 requirement minus 0. That's it. And the integral remains. And the integral remains. I'm sorry, I have so little space here, so that my writing may become cumbersome. And that's it. So we are done with this integral. And what we obtained, we reduced the requirements for the smoothness for both function p and our function u. Earlier, it must have been twice differentiable, the function u. And now, we only need that function u is once differentiable. Right? And p of x must only be integrable. And integrable functions is a very wide set of functions. Almost anything is integrable. So even if the function is like this, even if the function p is like this, is like the step, it is still integrable. The integral exists, right? Okay, so let us write the final equation that we obtained. Let's write the final equation. Okay, so what we have? First we have this integral involving the derivative of our unknown function and the derivative of our weight function, which is actually known. We choose it by ourselves. Then comes all the rest, plus, I will move it in one bracket, q of x du by x v plus r of x u v. And that's it for the left hand side dx. So these guys we don't know, we can keep them in the left hand side for now. HL multiplied by UL by VL. So here we don't know U of L. That's why I keep it in the left hand side of the equation. Okay? And these guys we know. We will move them to the right hand side. Okay, what we have in the right hand side, integral from 0 to L of fv dx. This guy minus eta L by v of L, v at the point L, and that's it. Did I forget anything? Hopefully not. Hopefully not. Okay, so let's talk a little bit about functional spaces again. What kind of integrals we have here? For example, we have an integral of a product of two functions here, right? One of them is v and another is our known solution. It says that this functional space must be at least consisting of those functions which are square integrable, mathematicians say. So function v must be at least this smooth. the square of this function must be integrable. So integral is not infinite, and it exists. We also have here the integral of the product of the derivatives of function u and function v, right? That means that these functions must have the derivative in some sense. I'm saying in some sense because I don't want to go deep into mathematics. Strictly speaking, these derivatives are not classical derivatives. These are generalized derivatives, so to say. По-русски это будут обобщенные производные в смысле пространства Соболева. So I said it, but I don't want to explain what it means. That's why I'm just saying to you that the integral of the square of the derivative of function v must exist. And that's it. These are two smoothness conditions that the function v should satisfy. And also actually our known solution should satisfy the same condition as well. Such functions that satisfy these two conditions, in mathematics, they are usually, this functional space of such functions is usually denoted like this, h1, 0L. 1 here means that we request the first derivative to exist. H here means that it should be a Hilbert space. Hilbert space. What is Hilbert space? Does anyone of you know what the Hilbert space means? Hilbert space of functions is a very simple thing. It is equivalent of Euclidean space for the vectors. If we have two vectors on the surface, on flat surface, what we can do with those vectors? We can sum them up. We can multiply them by some number, either, by some number, let's say that, and we define the inner product or scalar product between these vectors in Euclidean space, right? This is very important, to be able to define the scalar product. So, with our functions, we already discussed this topic about scalar products. What means the scalar product between two functions? It's just an integral of their of them multiplied. That's it, right? We already defined the scalar product. And such linear spaces where the scalar product is defined is called Hilbert space. That's it. So it's just why it was introduced. It allows us to operate with the functions like if they were vectors in a flat surface. Multiply them, multiply by a number, and add one to the other, and so on. And the result will be guaranteed to live in the same space. Okay. So both u and v must be elements from this Hilbert space. And you know now what it means. These integrals exist. And the scalar product is defined. Okay? And let's recall another condition for the function v. Function u should not satisfy this condition. Function u has its own condition on the left hand, right? So function v should not only be the element of this space, but it should be an element of a subspace of this space. This h10 is a smaller set of functions, only those that satisfy these conditions plus this condition. Okay? And for convenience, let us also introduce this space. These are functions from this space that satisfy this condition. Okay? the letter E here is essential. It is the word essential because people call this boundary condition essential. Why? Why? Because you already see that we already satisfied the second condition in this equation. We used it, right? In our equation, in our integral equation, the second condition already exists. We don't need to do anything else to satisfy the second condition. Okay? In this sense, this second condition is considered natural. Естественное ограниченное условие, natural boundary condition. Okay? But we have to do something to satisfy the first condition. Okay? That's why it is called essential. And this is the Hilbert space of the functions that satisfy the essential condition. So our solution must belong to this space. Okay?
So it means that in the space there is this functions of this condition.
If I take any function from this space, this function may not be the solution of my equation, but I will be sure that it satisfies this condition. Okay, so I will be looking for solutions only among those functions that readily satisfy this condition. Okay, and similar thing about v. V is any function that satisfies these two conditions, and I know from the beginning that they satisfy zero condition at this point, or points if there are more than one point like this. Okay. Okay. So this is the general procedure, and this procedure leads not only to the finite element method, but also to the spectral methods and some others. And now to move to the finite element method, I have to approximate these spaces somehow. Since these sets of functions are functional spaces, they are their dimension is infinity. So I don't know how good you are in mathematics, but any of those functions can be represented as a weighted sum of other functions, but which are called basis functions. But the number of those basis functions must be infinite. It's an infinite sum, right? When we want to solve our problem numerically, we have to restrict ourselves. We cannot work with infinities, right? We will need to choose some subset of basis functions, fix it, and represent our functions as a sum of only a subset of basis functions.
So for each Hilbert space we choose subset of basis functions.
We can think of the general Hilbert space. Yes. Yeah. Let's see. What can I delete? This equation I will need, and everything else I can delete. So these nice words, Hilbert spaces, vector spaces, and so on, are very simple by their meaning, right? I just explained what they mean, nothing more than that. So please don't be afraid of the words functional space or Hilbert space. Okay. So let us start reducing the dimensionality of our problem. This is the infinite dimensional function space, and I want to introduce another set of functions, sh. How do I define them? Let's take our axis. And as usual, let's introduce a mesh. Let's introduce a mesh. Say from x0, x1, x2, xn minus 1, xn. And let me change it here a little bit, the picture. Let's take the node I, the node I minus 1, and the node I plus 1. Let us introduce such functions that take a value of 1. Let's call this function phi I. This function phi I, it takes the value of 1 at the node with the number which is the same with the number of the function. And it takes the value 0 at all other nodes of our mesh. And it changes linearly between the nodes. So these are all conditions that I have to say that defines this function. So this function is extended like this to the ends. So we need to understand that this function continues here, but it is the 0 everywhere except for this and this interval. So I would have also functions here. So this is gonna be phi with which index? What would be the index of this phi? 0. We start from 0. This is the node number 0, so that it corresponds to the function phi 0. Okay, do you follow? And this function takes the value 1 here and 0 everywhere else, except for this interval where it changes linearly. So we connect this 1 with the 0 with a straight line, with a part of the straight line. Okay? So let's also draw. I don't have the red marker, unfortunately. I'll have to do something like this is another function. What is the number of this function? Tell me, please. Phi I minus 1. Yeah. So, and I say that these functions can be used as a set of basis functions. So if I introduce a set of functions phi I from 0 to n, I will call it the basis. A basis for which space? This is going to be the basis for the finite dimensional space of functions in which I want to search for my solution. Okay? So, what means basis? It means that any function v, I have to say VH, because it is already finite dimensional, it's not the same thing with that V, can be represented as a sum of these functions phi multiplied by, let's call it coefficient Vi, by the coefficient Vi. Okay. For I from 0 to n. And as an analogy to this notation, I will define also the set of functions VH that belong to SH and also satisfy zero condition at which point? At point x equals to 0, where I have this essential boundary condition. And as you can imagine, I will also define the set of functions that satisfy my first type boundary condition. So these sets are for sure parts of respective Hilbert spaces. So the functions that can be expanded into this basis, with respect to this basis, also belong to those Hilbert spaces. They are also integrable and they have square integrable derivative, at least partial. Okay? So the derivative may not exist in these points, but it's nothing for us because we are integrating, and these points are just finite number of points. It is even smaller than countable. Right? It is finite. Okay, what do we do next? Next, we represent our approximate solution. We will not say function u small, because u small is a solution, is the exact solution of this weak, I forgot to introduce one term, weak problem formulation. This integral equation is called a weak problem formulation. Слабая постановка задачи. Ослабленная. Понятно, да, почему ослабленная? You understand why it is called weak? Yeah, because instead of requesting that we satisfy our equation in every point, we are taking integral and just request that the integrals are equal. Okay, so we are weakening our conditions. So, and the exact solution of this weak problem formulation is denote u small. But now we are trying to construct an approximation to the solution of to the real solution, an approximation to u small. So u small is what we want, but we can't get it immediately. We need to construct an approximation, and this approximation will be constructed like this. It will be a linear combination of our basis functions that we chose. Okay. What should we do next? We should substitute this form in which we are trying to search for our solution into the integral equation. Replace this u with this u capital, or more exactly with this sum everywhere. Follow? This is one thing. And another thing, we can do the same with v actually, right? But with v, it is more convenient for us. It will be more convenient for us not to substitute this type of expansion here, but just say, since these functions phi form the basis, then I can request that this whole equation is satisfied for each of the functions phi I from this basis separately, and have n plus 1 equation instead. Okay? So I say that my v is equal to phi 0, then I say my v is equal to phi 1, and so on. And put this phi 0, phi 1, phi 2, and so on, into this equation. So I will have many equations instead of one. Okay, let me do this. So I'm substituting the sum into the integral. Let me do one thing right away. You know that the integral and the sum are both linear functions. Hopefully you know that. And we can change, first of all, we can change this sum and this derivative, exchange the order of the summing and the computing the derivatives, right? Yes, I don't feel that you understand. It's important. That's why I should stress this. I will change index for the moment, just to avoid that indexes mix. I will use j here, from 0 to n, by dx. Here I promised that I will put my basis functions instead of v, one by one, right? Okay, and I will skip the rest of this integral. It's straightforward to put everywhere instead of u this form, this expansion, right? So what do I get here for this integral? I'm saying that I can exchange the order of differentiation and summing. Is this clear? And then I can exchange order of this integration and summing. Okay, again, right? That is how I take these coefficients out of the integral. Because they are just constants. These coefficients are just numbers. G from 0 to n, integral from 0 to L, P of x. And here in the integral I only have, what do I have? d phi j by x, d phi I by x, dx, plus and so on. By and so on, I mean this tail. Okay? And let's write the right-hand side. We have the right-hand side as well. So in the right-hand side, instead of v, we put what? Phi I. Integral from 0 to L v remains unchanged, v of x, by phi I of x dx minus eta L. Instead of v, I am putting what? I'm putting phi I, as well as in the rest of the equation, phi I of L. Okay? And one important thing that I have to take care of is this term.
But phi I of L is not
What do you say?
phi n.
No.
Zero.
Let's recall what I've said.
Okay, zero.
I'm putting my basis functions into this equation instead of v everywhere, one by one, and I'm getting many equations.
So it is
So let me continue here. E from I, from and from what? From what? Tell me. From 0?
No, 0 is equal to 1.
From 0 or from 1?
1.
Why from 1?
0 is always 0.
Function phi 0 does not satisfy this requirement. You see?
Yes, yes.
It is not equal to 0. It is not equal to 0 at this end.
Yes.
So it does not. It shouldn't be taken as the test function. That's why we start from 1, and let's discuss the same thing about the last function, phi n. Does it satisfy this? We don't need it to satisfy this condition actually. We don't need it. That's why we take it into the set of functions. Okay? We exclude only one basis function from here. And in this sum, we don't exclude anything. We use all the basis functions in this sum. Because we don't need such specific requirements for the function u. You may ask me about this requirement, right? But it can be easily satisfied because phi is equal to 1 at the left point, at the left point of my domain, right? Phi 0 is equal to 1. You follow? Phi 0.
How they can simultaneously do
What?
like the first, I think, I thought that this is for different functions. The as space as h0 and as h because
These are different functions for sure. These are different functions. Our solution, u capital, should belong to SHE.
yes.
But our test function now should belong, our test function in finite dimensional space should belong to SH0.
Я просто сказала, что вы сказали, что там T1 должна равняться v функции v. Ну, сейчас вот говорит, что phi должно satisfy the condition.
We'll continue. Thank you very much.
Ну, потому что функция phi должна удовлетворять равенству T1.
Function phi is already defined. The functions phi are all defined already. We don't change them, we don't request anything from them. Okay? Phi 0 is equal to 0 at this end, at this point, left point of our domain, right? Is equal to, oh, sorry, phi 0 is equal to 1 at this point of our domain. That's why we can satisfy this condition for our function u.
So,
For you, okay.
so
Okay.
I think we can change not the v because the v is different with this v.
But phi function y doesn't should satisfy condition for your function because it should satisfy the conditions for v function.
I'm not sure I follow your question.
Почему просто функция phi должна удовлетворять условия для функции u, когда мы...
No, I didn't say that. The function v should not satisfy the conditions for function
Нет,
u.
phi, почему мы говорим, что phi должна удовлетворять условия для функции u, когда мы заменяем функцию v на phi. То есть phi и u никак не
Those are
связаны.
different v. Yes.
U capital is an approximation to our unknown solution. We have a sum of some free coefficients. They are free for now, these coefficients, by our basis functions. If we take from this sum, if we say all u capital I are 0 except u0, then we can satisfy this condition by setting u exactly to t1,
Yes.
right? So that's it. That's why we don't need to reduce this sum. Okay, we use all points in this sum, but we don't use all points here. This is important. And I didn't take care of this term. It is different from the rest of the terms in the integral. That's why I have to take care of this. Where should I write it? HL. U. What is U? It is a sum. It is a sum by J, Uj, capital phi J. At which point? At point L. let me ask you, how many phi j's are different from 0 at point L? Only one. That's why from this sum only one function will remain. Do you see it? No. Phi n is equal to 1 here. What is phi n minus 1? Here. 0. What is all other functions at this point? 0. That's why from this sum we will only have a u n and phi n. Okay? Which is equal to 0, by the way. Well, equal to 1, by the way. Sorry. Okay. And what else do we have here? We also have phi I. I will keep it for the moment, but you see that it is also calculated at point L as well as here. And you see already that this term will only remain when I is equal to n. Right? Here and here. So these additions are only present at the last point. In one equation, only in one equation of all. Okay? Only this in this equation. With I being equal to n. Is it too hard to understand? Or do you get it? Okay. So this is plus, and this should be put here.
But why we don't have vi? But why we don't have vi? It's not vi modified.
V?
No. Why the v is not like the u have the vi modified phi I? Where is equal to 1?
I'm sorry, I don't understand the question. Could you please write it down on the board?
Well, we don't have vi because it should be like the same.
This is the general form of any function that defines this set of functions.
Yes.
This letter V does not have any connection.
Yes, I know it's
with-
w.
I can call it W or anything else.
Yeah, I know.
So, what's your question?
Question is, u is like the v, u is the uj phi j, but why v is not the vi phi I?
Are you saying why I am not using this expansion?
Yes, just why we should only use phi I? Yes.
You want me to put this sum here? I explained I can do this. I can do this.
But it's also okay.
But it is more convenient for us to replace this one equation with many equations. In each of them, we just say v is equal to phi 0, v is equal to phi 1, v is equal to phi 3, and so on. And insist that each time this whole equation is satisfied.
Oh, okay.
Okay?
Okay. I know.
Any other questions? Any other questions? Because we are almost done. With this formula, where is the formula? So, I'm sorry. The board is so small that I don't know how to deal with this. So, here is the formula. I will delete everything I don't need. Mark the formula, the final equation, so to say. No, too much. Sorry, too much. Yeah. Maybe I should rewrite it. Otherwise you wouldn't see the idea. G from 0 to n. This integral from 0 to L, where we have p of x, d phi j dx, d phi I dx, plus, and I will use all the other terms so that the formula is full, complete. D phi, which j, right?
Yes.
Do you follow this? It's important to follow. R of x, phi of j phi I comes from these two terms, from these functions. Dx, and this is equal to, I will move this term to the right at this point. From 0 to L, f v phi I dx minus eta L phi I of L and minus, is it h or eta? I'm sorry. It was
H.
It was h. It is h. Heat transfer coefficient. U capital N phi N of L, which, well, I can replace it with 1 with unity, but I'm keeping it just to keep connections between various formulas. And phi I of L. And I guess this is it. So now I can delete.
Вроде бы x забыли.
Что?
Вроде бы x забыли, там где по x. Да, можно.
No, because I put brackets here, and this is 1 dx for everyone.
Can you explain why the master is phi I not phi n? Because this is the same. The master phi I. The master one.
The last one is what?
It's also is the phi I not the phi n equal to 1. Yes. Like this, yes. But
This guy, most of the time it is equal to 0, except for the case when I is equal to n.
yes.
So in all equations but one, this term and this term vanish.
Oh.
In all equations except one,
Oh, yes.
except the right hand side,
Yes, yes.
it vanishes. This term becomes 0. So, what do we have here? Who can tell me? What kind of system? This is the system of equation, first of all, right? Of equations. What kind of equations we have here? Is it differential equation? Really? Do you know this function? Yes. Can you differentiate it? Do you know this function?
So it's linear.
It's a set of linear equations, like in school, right? It's a school problem. Because everything under the integral is just a number. Sorry? Yes, it is just a number. We can calculate this number. We know everything under the integral. Know all the functions. Right? The only thing, or only things that we don't know is the set of these coefficients. And if we find these coefficients, we will be able to represent an approximation to the solution in this form. Okay? If we find coefficients u capital J, then we'll be able to write our solution obtained by the finite element method. Okay? So our goal now is to solve a system of linear equations, linear algebraic equations, and get these coefficients. Is it possible to solve this system? Can we solve this system? Not technically, but in principle. We should check determinant. Yeah. Nice. If the system has 1 million or 5 million equations, good luck checking its determinant. Because checking the determinant is the problem even harder than solving the system. Yes, you're right, for sure. We have to ensure somehow that the determinant is not zero and the system is solvable. But nobody computes determinants to do that in real life because it's too complicated to compute the determinant. I'm talking about a different thing. How many unknowns there are in the system? Please count again. N plus 1. N plus 1 unknown. How many equations? N equations. What your experience tells you? Why? Everything was so nice. Why can't we solve the system? What are we missing? We need another equation, one more equation, right?
We know that U0 equals
Cool.
C1.
Cool. Plus 1 equation from essential boundary conditions. Namely, u at point x equal to 0 should be equal to t1. Or, in other words, u capital is what? Is an expansion. Like this, okay? And since this guy is equal to 0, the argument for the basis functions, how many basis functions are not equal to 0 at this point? Only one. Only one, which means that it is equal to phi 0, u0, which is 1. And this guy, u0 should be equal to t1. So this is the extra equation. u0 is equal to t1 is another equation that we need to use here to close this system. That's why we need to do work to make this happen, right? And that's why this is an essential boundary condition. We don't need to do any extra work to satisfy the second boundary condition, but the first we need to do work. That's it. We obtained the system of linear algebraic equations, and at this point you know what to do. You just need to calculate these integrals. There is another nuance here. How to calculate integrals if the functions r, q, and p are not defined up front, or they may be non-integrable analytically.
But numerically?
Numerically. Cool. So we calculate these integrals numerically. And in the context of finite element method, the usual approach to take integrals is to use Gaussian quadratures. Quadrature. Квадратура Гаусса. Не знаю, слышали вы про такое или нет. Один из методов численного интегрирования. Gaussian quadratures is an alternative to more well-known Newton-Cotes methods. Ньютона-Котеса в квадратуре, типа прямоугольников, трапеции и прочее. Это Ньютона-Котеса, а мы говорим про Гауссову квадратуру. Gaussian quadratures are specific in the sense, I'm sorry that I'm speaking Russian from time to time, but I need to explain. So, Gaussian quadratures are different in this sense. For typical quadratures, we define our function values at the ends of our intervals on which we split the domain. We split the domain into intervals and we compute the values of functions in the ends of these intervals, usually in typical quadrature methods. In Gaussian quadratures, another approach is taken. The function is calculated inside each interval at some specific predefined points, at some specific locations. Okay? This allows to increase the accuracy of integration because we have more freedom in choosing where to compute our function. Okay? And the Gaussian quadrature is just some weight coefficient by the function value at point xk, and these points xk, how they should be chosen, it is tabulated. For example, if we want to take say 3 points of Gaussian quadratures, and by the way, I should have written integral from 0 to 1 here, from 0 to 1. The Gaussian quadratures are usually defined at for some canonical intervals, from 0 to 1, for example. And to use them, we need to convert this integral to canonical coordinates, but this is easy. This is a linear transformation of coordinates, right? When you do this, don't forget about these differentials. When you apply linear transformation of coordinates, this differential will give you the length of the interval as a multiplier here, and in the denominator twice here, 1 by h squared, the length of the interval. Weights and second, I will reproduce a part of this table. So xm and weight K and WK. So this column will say at which point between 0 and 1 I should take my value of function. And this column will say what weight coefficient should I use in the sum. Plus 1/2, 1 minus square root 3/5. This is the first location, and this guy is 5/18. Then the last location is symmetric to the first location, and the coefficient is the same for sure. And in the between we have 1/2 and 4/9. That's it. So 3 locations inside the interval from 0 to 1 are taken, And at these locations, we need to calculate our function. This method allows to integrate polynomial of order 2m minus 1 exactly. If we take m equal to 3, then we can integrate polynomial of fifth order exactly. Exactly. So with remembering about the rounding errors for sure. Rounding errors will be present, but otherwise there will be no error term here. Okay. If you take the polynomial of higher order as function f, you will not be able to integrate it exactly with m being equal to 3. And if you take exponential function, you will also not be able to integrate it exactly. Okay? That's it. Questions?
Yes.